I'm about to take over as head of maths at Mottawaka High School. I've been there for the past year. I was 19 years at Nelson College before then, in the UK before that. Also this year I've just begun working for the Kahoiaka as like a numeracy support, so it's been a slow start, but basically I am available to come into your schools and speak to staff members and try and upskill and everything. And so part of what we're trying to do here, as Mike said, is this is almost marketing, this kind of spiel. Hopefully there'll be enough from this that kind of interest you and make you realise that there's some value in what we're talking about, and that it will tweak and nudge some of your thinking that I believe will actually have some really quite significant influence, impact. I don't like using kind of marketing terms, but it will be good. It will actually help your students understand maths. It will make them more confident, and hopefully this is fundamentally make you more confident. One thing I'm just going to say, because I've endured many lots of PRD over the last 30 years, so I'm going to talk about this, which obviously you've all got your own copy of and you refresh every couple of weeks. Don't you like it? The point is, this is all in place. I don't actually need to talk about this because you're expert teachers. I've gone into lots of schools, I've seen lots of classes, all of this stuff is actually in place. All I really want to talk about, and I'm going to hopefully cover some of it, is just these little 7 post-it notes. It's these little tiny bits of teacher knowledge and teacher confidence that I think are missing from maths education generally. Specifically, it's not really in teacher training education. And there's hopefully let's start that process of filling in these gaps. That's the plan. Okay, so the first thing we're actually going to do is we're going to have a little question, and it's audience participation. No one's allowed to not be part of it. Have a quick read. Take a thought. If you think it's A, go and stand over there. If you think it's B, go and stand over there. Off you go. Now.
Oh, hang on.
Really quickly. Blink response. No one can stay in the middle. Shall I read it out?
No, sorry.
Okay, move. Go. Don't discuss it. Just stand up and move. You can follow other people if you want and see what you think.
Are you standing there?
If you think A is the answer, just stand over this side of the room. If you think it's B, stand over there.
So don't relax.
You're not allowed to not think.
Oh, God.
B.
Yeah.
Okay, I'm going to
This is B.
Come on, Mr.
I've seen this. This is in.
Okay, no, just go and.
Yeah, but I
stand
can't
somewhere.
remember. It's in
Don't do that year 10. I know this one.
Is this A?
Yeah.
Yeah, sorry.
I'll go there.
Okay, right, second part. Now that you've seen where people are standing, does anyone want to change their mind? This is like run around, if you're English and my age.
Run around now.
Yeah. I'm not going to do the accent, but anyway. So, if you want to quickly change your mind, do it now.
Yeah, I didn't read much.
Well, they're the smaller groups. I can't go over there.
That's fine. Cool. All right, well, tell you what, take a seat and we'll quickly talk about it because I know it seems a bit silly, but this is actually really important. This question is actually quite a famous question, and it's an example of what's called the conjunction fallacy or the narrative fallacy. And in fact, A is far more likely. Far more likely. In fact, by several thousand times more likely that A is correct rather than B.
Yeah.
But don't feel bad, because if you chose B, it actually just means you're human. Okay? We are hardwired as human beings to accept the version of reality that makes the best story. Okay, it's actually why we've survived as a human race. Because we support each other, we listen to we can get enthused, we can go and pick up a stick and jump in front of the saber-toothed tiger just because someone told us to. There's all of these things that if we were actually born completely cold and rational like Mr. Spock, we would have died because we wouldn't have formed social groups, we wouldn't have had social bonds, and actually our society would have collapsed. So it's a bit weird. Actually, about 70% of people generally choose the wrong answer for this question and this type of question. And it's nothing to do with age, it's nothing to do with ethnicity or nationality or gender or even education. It's actually if you're caught off guard and you're given some information, you choose a story. And it's just how we are. So nobody is born mathematical, nobody is born rational. We actually have to learn these things. It's the only way we actually are going to get that knowledge. Now, I think it's fascinating. Like, you could actually talk just about this concept for hours in itself, and they would. But specifically in maths, this is hugely important. It's a real double-edged sword in maths education. Because as you know, as teachers, if you have a story, if you have a context, if you have some sort of idea, you can grab people's attention, you can get them involved, you can get them enthusiastic. It's a good way of starting stuff. But the problem is, a story will create a story. Your students will create a story inside their own head of what it is they're doing mathematically. They'll create a kind of narrative around it, and they will stick with it, especially if it makes sense to them at the time. It doesn't have to be rational, doesn't have to be logical, doesn't have to be mathematical. It works for them, and they'll go with that. And especially if it gives them short-term success. What was the one you were telling me about?
No.
Oh no, the adding on the zero.
Yes, yeah, so adding on a zero, students, I know that if I multiply by 10, I add on a zero. And someone's told them that, you know, a friend's done it as well, and it becomes their story and their reality. But we know that as soon as you go to 0.9 times 10, things are going to change. And so, yeah, the stories can misconstrue the
But not
thoughts.
even that, what does adding zero do to a number? Doesn't do anything to it. But we're saying add on zero, and it's just,
Yeah.
the
Adding
whole
zero
thing is a
means
complete
add
fiction.
nothing, yeah.
But I would say, for that particular context, in high school as well as primary school, that is the single most common explanation I get from students. So inside their head, there's some kind of narrative that has...
And even just thinking now, you know those students that you've explained something to, and you think it's quite a simple concept, and they keep coming back with you with something quite random, and you can't really understand their understanding. It's probably because they've got a story that's cemented for them. And I suppose it's our job, if we do come across that, to actually think really hard, what the hell is it that they've been suggested to them for them to stick with it?
And the other thing, of course, is it's not a primary school thing, it's not even an early education thing. I mean, James and I and Linda, we have things called quadratic equations. Oh, you do the opposite of the number. The answer's 7. No. You know, I mean, I won't go into the detail, but they have created, even as teenagers, this completely warped view. But throughout year 10, it was probably working quite well for them until the wheels fell off, and then they're kind of bereft. So that's the first thing. And actually, we're just going to jump to the next one quickly now, because have a read of that. What does it say? Oh, yeah.
Yes, that's great.
Yeah.
So most maths
Most about something, that's fine. Something's good.
is based
Yeah.
in this approach for leaving of something and any information that isn't considered necessary for understanding. This concept is known as redundancy.
Perfect. Didn't get all the words. Does it matter? No, because the meaning was clear. Now, this concept of redundancy is huge in computer science, it's huge in linguistics. And this is an example of it. All I've done is I've taken out the vowels. It's not the only version of redundancy, but the fact is, all written languages or computer data can actually be stripped of information, and you can still make sense of the gist of what's going on. So long as you fully understand what the system is that you're trying to get the stripped information from. So if we can all read English, we can make sense of that statement. I would suggest that if that was in Italian, unless there's an Italian in the room, we probably would have no idea. Okay? But the idea of redundancy, if we have knowledge, we can actually make sense of what's going on. Now I say this, every language has redundancy. I think most of the English language, it's about 50 to 60% of the symbols or letters can be removed, and a native English speaker can probably make sense of it. There is one language, and I'm going to use the word language, in the world that has no redundancy in it. Everything unimportant has been stripped out of it, and that's mathematics. However, who decides what's not important? Mathematicians. People have already gone to the end of the process, and they know that's not important, or we can leave that out. But if you don't know what you don't know, how do you know it's not there? Not that it's not there, it's just not written down. That's even more confusing. And some of it can be quite simple.
What?
I'll just do this one. Then you can go up. So we're quite happy to talk about centimetres squared, because that means it's a two-dimensional area. We'll talk about centimetres cubed. You write centimetres with the one-dimensional, because mathematicians say it's not important. I actually think it's really, really important, because that one, and it's nearly always ones that are removed, ones and zeros are taken out all the time. That one explains exactly what that centimetre is referring to. Yet we're using it as a label for something rather than as a description of what we're doing. It's that slight tweak. Okay. Now again, I don't want to go too far down because this. What was the one you did?
Oh, the one that you showed me, which is if you've got, we all know that as an unknown, but then it can also be called that, and it can also be called
That's
that.
one of them.
It can also be called that. Is that right?
Yeah, absolutely.
Yes.
All of those ones are absolutely there. They're all there. It's so when the x squared appears, it's not come out from nothing. The one has been raised up one power to 2.
And you get something like that, and you think, ugh, but it's because we've only been addressed with the x like that, because it's not
Yeah.
really.
Okay.
Yeah.
No, again,
Sorry.
I'm really just saying that this is kind of slightly esoteric, and you might even think even perhaps irrelevant. But the point of what I'm trying to do today isn't to teach you something right here, right now. It's just to make this idea, make you aware of this idea. And once you see it, you'll open up any kind of textbook or any worksheet, or you'll watch someone, you'll hear someone, and you go, hang on, as it's happened to you, I believe,
Yeah.
Mike.
So I know there's lots of things that happen. Recently for me, it was when I looked at it was a New Zealand maths lesson or series of lessons, and it was about fractions for some of my guys that just needed a bit of pushing, and it was the idea, and this, you know, this is again about our knowledge is really, really important. It was the idea that half is a number, and half is, or halving is also a process. And when I thought of it like that, I thought, oh, crikey. So when we say to children something like, that's half, and then you go, I'm going to half that, you can sort of understand suddenly, you can see where the, you know, things are getting circled around really quickly because of what we've said. And we, you know, say it sort of harmlessly enough, or we think we're saying it harmlessly enough, but have I made clear enough to my students over the last 25 years that this is half a number, or we're going to do a process of halving?
Well, we'll circle back to fractions in a moment.
Yeah, we
So,
will.
should we just,
I
just noticed the time. I think.
I did have the other ones about that as well.
Well,
about
we'll
the why.
talk at the end.
Yeah, about the why. But it's, yeah.
Sorry,
carry on. Go.
Yeah, just going to quickly share a story. You know, in the good nature of the Linda problem, bring you in with an anecdote, which is my very, very, very first few minutes of teacher training. So Reading University, as it was, walked into a tutorial room. Me and the other 8 prospective maths tutors were there, and our tutor walked in and he said, right, we'll do introductions in a minute. Just please, in your head, work out 17.5% of £20. Do it now. He said, okay, now first of all, who was nervous? Okay, remember that feeling, that's going to be useful. He said, secondly, as best you can, write down how you got the answer on this post-it note. So screw it down, put it up. I said, put it up on the wall. Everyone have a look at it. I got it right. And everybody got it right. She said, okay, what do you see? And we saw 9 completely different ways of getting the answer. And she said, okay, take a seat. He said, you might think the fact that you have 9 different ways of getting the answer is the important thing. He said, that's not. The actual really important point that you have to take on board now is that none of you did 0.175 times 20. He said, however, and then she picked up a big pile of textbooks and dropped them on the table. These are the top 4 best-selling textbooks in the UK. They all had a little piece of paper, and turned to each page. That was exactly the technique. That was best practice for that sort of question, according to the textbooks. So what she said to me, and I'm just sharing it now because it was such an influential feature of my progress, is she said, you have gone through a process that you have actually succeeded because you've rejected it. I hope you can follow that. The way that you were taught, you've actually, by luck or by judgment, got through it, and you've dropped it off, and you've actually left it alone, and you have actually understood why things work, and you can get answers, and you have actually stopped or not done what you were taught to do. He said, but there are very, very few of you. And in fact, there's even fewer of you, given that you actually want to go back and be teachers yourself. So please, 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 just be mindful of this and don't repeat it. And that was really fundamentally for me, everything that from that point on, nearly 30 years ago. I hope that didn't sound too egotistical, but I think for me it was such a pivotal moment. Everything I try and do in the classroom, it's a lofty goal, is I try and teach why something works, not how it works. I was taught how to do maths. I was taught, here's the question, here's how you get the answer. This is the problem, here's how you get the answer. These exercises, this is how you get the numbers that match the one in the back. And that's it. And I hated maths at school. In fact, my ex-teachers can't believe they couldn't believe I became a teacher. It's like poacher turned gamekeeper. And they also couldn't believe specifically I became a maths teacher, but I absolutely love it. And it was through luck. And I'm hopefully this could be the beginning of it not being luck that people enjoy maths. That's my aim. So, I'm rambling. Sorry, I'm going to keep on. This is actually on to you now, Mike.
It is. Rob's, Prophet White's research, and there's a Zoom going on at the moment, and I know there's a few of you that have been working with him over the last couple of years. And his research, a large proportion of year 6s and 8s get this wrong. So what I want you to do just with the people around you is, what is the usual wrong answer or answers that year 6, 7, 8 students give to that there? What would be the usual wrong answers? Have a chat. 1 minute.
18. They've got 18 underlined. They still do it in year 9, don't they?
Or the other option is they put 4
Possibly.
and they ignore the plus 10
They kind of
at the end. They just ignore the rest of the equation.
What did year 6 put there then?
18.
Oh,
They still do it in year 9.
Oh, I see, because they just did look at
Did you edit it?
There's another one that closely follows it. It's actually one answer.
I've had that numerous times this
Well,
year.
another wrong answer.
They don't balance it.
They don't
So they,
understand.
they'll only read part of the...
Okay.
Even when you've explained it to them, they still don't really.
Even with M&M's.
Okay. Well, tough. Okay.
Well, we'll
Right,
pretend
move on.
to understand with the M&Ms.
Okay.
Oh, what are we going to do this table here? 18, yep. Why?
Because they read it like from start to end and don't realise that equals is the same.
Okay, cool. Anyone else with a different one?
Could be 4.
Yeah, 4 plus 4, maybe 8. Yeah, let's sing that.
Yep. In fact, my favourite one is 5, because they see a pattern of halving. 8 becomes 4, so 10 becomes 5. Everyone knows that, that's obvious. So the thing is, but all of those are stories. And they're stories that are connected. In fact, sorry, there's another slide, isn't there?
Yeah. Cool.
Oh, yeah.
What's that? What's going on there?
They're solving a problem, but rather than doing it step by step, they just keep going across.
Is it like Vietnamese?
Sort of.
So, okay, so the question is, if you were asking them to explain what they were doing, how would they say it?
Okay, well, 12 plus 2 equals.
Yeah, left to right.
Yeah, yeah.
Yeah, like a story. Yeah. Like, yeah. Yeah.
Yeah, 12 plus 2 is 14. You add on 6 and the answer is 20. You then take away 5 and you get the answer 15. Sweet. Can I have a tick, please? Because that's what because it said 15 in the back of the book, so I must be right. Okay.
Right. So that leads to this next one.
You would mark that wrong because the syntax is wrong, would you?
Well, that's our next question. What's that? Same as, balance. Other words? Equals, yeah, okay. Give you that.
It's the same as.
Same as,
You
Yeah.
use makes,
makes.
Makes,
All right, yep.
which is
Okay. Answer is?
it's a,
Yeah.
Sorry?
it's 11.
Okay. Answer
What were
is.
those?
This now you're actually going to explain why I've been holding the stick for the last hour. This is actually, by the way, the best teaching tool I've ever had. This is my third stick, by the way. I've had one for about 27 years, I think. This is my favourite one. The other two are in retirement. And I use it all the time. From very first lessons with my year 9s, all the way up to my year 13s, and even when I've taught scholarship or STAR course for university first year, this piece of wood comes out. We use it all the time. Multiple uses, but again, another anecdote. When I was last century doing my teacher training, I had to do as part of it a piece of survey. I had to do data. I had to actually research. That's it, research. I had to research something. And I was at a large year 7 to 11 comprehensive school in the UK, and the UK numeracy strategy was rolling out, and we were all being told that all teachers are teachers of numeracy, which I think we're all familiar with as a phrase. And I was actually really lucky because I was able to survey the teaching staff, which I can't believe they let me do it. It was really, really valuable, and without doubt, one of the questions was actually that, what does it mean? I did say, without using the word equals or equivalent, what does this mean? And by a country mile, the answer was the most common statement put down, which is unfortunately completely wrong, for the reasons that we've seen in those previous slides. Currently, a lot of students come in and they'll say it's the same as it's balanced when we're talking formally, and that's awesome, but when you hear them then describing their work, the answer comes in. They default once they're working back to the story, back to the narrative. So, what are you looking at?
Talks.
Not physics.
Absolute equivalent. Talks, moments, yeah. Balance. Okay, so it's balancing. Why is it balancing?
The answer is
Well, there is an answer, I'll give you that.
Because it's equivalent on both sides.
Okay, so it's the same on both sides.
What is?
Equal weight, cool.
The weight's at the centre, it's where your thumb
Weight
is,
to
where your
centre, where
finger
the
is.
finger. So, both sides of the stick are the same, agreed? They're not the same.
They're equivalent.
Oh, okay, so in what aspect are they the same?
The
So this is how I teach the class, I'm not meant to be patronising.
And same with weight.
Same with weight,
Not
yeah?
Same with length.
Oh, yeah, basically. So this stick is the same and not the same at the same time. And this is actually what the equal sign really, really means. The equal sign brings together two, or okay, we'll stick with two, pieces of mathematical expression that have the same value but different appearance. And the value and the appearance of what you're dealing with is very, very important. So we've got these three statements up here. So if we start with the one in black, 12 plus 7 has the same value as 15 plus 4. Hopefully everyone is, or is the same as it's balanced with. The language is fine, just not the answer is, please. So imagine how have I transformed the black statement into the blue one.
So you just shifted part of the left side
Yeah.
without changing the total.
Without changing, yeah, absolutely. I've changed the appearance of what I'm dealing with. So on the left-hand side, I didn't have 12 plus 7, and I've changed the appearance of it to 10 plus 9, but I haven't changed the value. But how have I gone from the black statement to the orange one? Doubled it. So in that sense, I've changed the value, because I've doubled it, which means I automatically also will be changing the appearance. So it's that duality of what it means is what's really, really important. And mathematicians will do both those things whenever they're working on something. And it's not just anyone doing maths. Sometimes we might change the appearance of something, sometimes we'll change the value. Changing the value changes the appearance, but changing the appearance doesn't change the value. 2/4 is the same as 4/8, agreed? I've just changed the appearance of what I'm dealing with. Okay? And obviously when I'm teaching algebra or stuff with my students, I'll actually say, what are you doing? You're changing the value, you're changing, and actually make them actively think of those two different things, just as I make them actively think about what the equal sign means. Because once that narrative takes place in their head, certain things will become clear. So, I think, was that the exact question I did?
Pretty much. So Kieran came into my room about a term ago and just chatted to the students about the stick and about the equals and threw that up on the board. And even when I think I put the question up there, what's your first impression of that? Some might get a bit squeaky bum and seats, others might go, oh God, that reminds me of 7th form or whatever it may be. And but then if you look at that equal sign and treat it with what Kieran's going to do now to it.
Without doubt, following on from the stick, the second most useful thing we can have in maths.
Alright,
What's under there?
12.
Wow.
Yeah.
Yep.
Something with the value of 12. So that's your start point. So you don't focus on, the number, guessing and check, that's because something times by 2. If I times by 2, I could try 10. 10, that's 20. You don't
Trial and error.
go down that trial and error way. You just say, calm down. And like my students, I get them to write a question mark on their thumb or on the back of their rubber or on a piece of paper. Or they then start to visualise it. Whatever is underneath that piece of paper, I don't care what it looks like, its value is 12. So that's where we start. And then, how about we move that other things off? Let's just start to be a bit more careful. What's got to be underneath the piece of paper?
4,
36.
Yeah. Again, I'm not going to get interrupted or taken off track by what it looks like. The value of what's under that piece of paper is worth 36. So let's just write that down. I've got something that's worth 36. Now I'm going to look at it. Well, it still doesn't look nice, but it doesn't matter. I'll quickly write it down. Okay. So what's under there? 44. Again, I'm not, what students are sort of, and again, you can understand why, they focus in on what's missing. That, focus in what's there. Don't get waylaid by the appearance, just the value. Whatever is under here is worth 44. So let's now take a look at it. And we've got a special small one I showed earlier. What's under there? 22. Okay. So the missing number is 22. Now, I mean, I've been doing questions like this a lot, and I actually, some of them still might do similar things, and students will do stuff like this all the time. But this is just a little bit of mental arithmetic and truly understanding what the equal sign means and its importance in the structure of maths. And that's what it is. That's actually what the question is, which could very easily sit in a year 10, year 11 class. But that and that are fundamentally the same thing. There's a bit of redundancy in the one up on the screen. For example, the multiplication symbol has disappeared because mathematicians don't use it. We know it's there, so we don't bother writing it down. And we don't use the division symbol. We turn it into a fraction, which becomes kind of tricky for the things that Mike started alluding to. So that's the first kind of takeaway, that thing about the equal sign. And, yeah, okay, should we just move on?
Right, what's that? Sorry? 3
Eights.
3 divided by 8, 3 divided by 8, yep, what else is it?
3 8.
3 eighths. Yep. 8.
3 over 8.
3 over 8. 3 out of 8. Out of 8. Cool. Right, got paper and pens there for them? We've got time.
I don't think we have time. We're supposed to be out here in 8 minutes, so we have to come to the chase.
You guys there, can you think of a visual that would represent 3 divided by 8? You guys there think of a visual for 3 eighths. You guys there think of a visual for 3 over 8.
I always like cake.
Yeah.
Go. 30 seconds.
Pixel cake. Yeah.
So these 3 pizzas, we've got to divide them by 8.
No, you've got one pizza chopped into 8,
3
and
out of 8.
you've eaten a bite out of 3 of them. Or
You can have
3 of them
you
are
can have an
gone.
8 each and I'll have 3. How's that?
No. bunch of it.
3/8, 3 out of 8, 3 divided by 8, 3 over 8.
So that's the,
Say if I took 3.
I don't know, the learned, for me, 3/8 is of that one whole,
Yes,
which is a learned thing, which isn't
which
necessarily
is, I suppose
right.
you're talking about the redundancy of one whole is the redundant bit.
Yeah. But you still say 3/8 of whatever, 24 or
Good.
Which one did Mike ask you to do?
Cake.
Sorry?
What's that?
Which?
3/8.
3/8.
3/8. What did you do for 3/8?
Cake.
Cake. I like cake.
That's why I did it. Yeah.
Okay, so, or pizza. Do you mind if I draw pizza? I'll draw
Yeah, pizza's good.
So, 3/8. Something like that?
Wait,
It
yeah.
doesn't have to be circle, but does everyone happy that's 3/8? Okay. So what else have we
What
got?
about you guys over there? What do you get? 3 divided by 8.
3 whole somethings, like
Yep.
3 whole pies,
Yep.
being divided into 8.
Okay.
All 3 have been divided. But
All 3 divided into 8?
No,
Yep.
no, just, no, we kept them whole, we kept them whole. But
Right.
3 have been divided into 8. How do I explain this better, guys?
We had, yeah,
Sheet, okay.
Sheet,
By
yep.
sheet, but they have the size.
Yep.
Yes.
So notice it helps to divide it into 8. You're right, you're trying to get it into 8 pieces, but dividing each piece into 8, then you can count those pieces for the, yeah, awesome, cool. So already we've got 2 different representations, and then over here with 3 out of 8, went with apples, and it was 8 apples taking 3 out of those 8. How did you guys go? Nah, shake. Notice with the shaking of the heads came with this 3 over 8. All it's describing is the actual fraction, what it looks like. It's right 3 over 8. It's like saying, if you want to write an M, instead of saying M, you could go down, off, up, down, and up, and down again, and down. That's literally what it's saying, 3 over 8. So mathematically, it's not saying anything. Okay, whereas you can see clearly from what you've drawn, or what you've visualised, these 3 have got worth.
And there is a lot to unpack in these 3 things, because we can only write that number, whichever one we choose to be, one way. That's our only option. But these are 3 completely distinct concepts. They've all got 3 distinct units. Now, first of all, there's some redundancy here. When we say 3/8, a fraction only means anything if we know what it's out of. So we should actually be saying 3/8 of 1 whole, or 3/8 of 1. That's why we've got the purple symbol. There's our 1. So we're starting it with a single unit. But 3 out of 8, which is a perfectly legitimate statement, and the symbolism is absolutely correct, means that we start with 8 things, not 1. If we're doing 3 divided by 8, which again, and mathematicians into high school and beyond don't use the division symbol, that it's deemed redundant. We use a fractional